Yeah, I'm going to go ahead and get started. It's 9:01, is that right? Yeah, 9:01. I think so. Anyway, welcome everybody today. Another PDHP workshop. I'm Paul Schultz, a statistician and data scientist here for PDHP, and I just want to welcome everybody here today. While everybody's getting settled in, I'm just going to say a couple words about our center before I hand over to our speakers. I know our time's valuable today. We always are, even though no one thinks they're going to ever go to 1 o'clock, we always end up running late, I feel like. So I'll try to keep this brief. So again, as you're settling in, welcome. Happy to have you today. I'll say a couple words about the population dynamics and health program that I'm representing today. First of all, I want to thank our founders. That's the population dynamics branch of NICHD, who pays for these kind of workshops and sort of backstops all of our work at PDHP. A couple of the program features that I want to highlight today are a formal mentorship program for early career scientists. We offer a free statistical consulting program for any of our affiliates. And we also have a team of data scientists, myself, Joshua Zhao, and Dr. Brady West, that can deploy onto your project and actually do paid project work for anyone who wants to outsource any of their technical work. So that's a little plug for our center. If you're here today, you've probably already hit our website. The URL on the website is pdhp.isr.umich.edu. So if you have any, if anything I just said kind of piqued your curiosity, it's all on our website. Feel free to look it up there. You can reach out to me directly, and I'm happy to interact with you. Any questions you might have. So in terms of the workshop today, we are going to be recording as always. So the video will be available later. If you've got colleagues that weren't able to attend live, you can let them know that the video should be online either this afternoon or tomorrow. That's the good news of the video. The bad news of the video is that you guys all have live connections, so anything weird or embarrassing you do might get picked up. So just make sure that you're muted by default, both video and audio for today. If you have questions from the audience, please feel free to send those by the chat. I'll be monitoring the chat today, and I will be, I'll be reading those questions as they come into the presenters. So I think that's the best way to get your questions in is to do it via the chat. I think that's it for today, and then I will introduce our speakers and we'll get going. So we've got two presenters today. One's Michael Elliott. He's a professor of biostatistics and a research professor of survey methodology at the University of Michigan. His statistical methods research interests include design and analysis of sample surveys, novel models for longitudinal data, and causal inference. And he works in numerous applications, including pediatrics, women's health, injury research, and social epidemiology. And our other presenter today is Yajuan C., who's a research associate professor in the Institute for Social Research at the University of Michigan. Dr. C's research focuses on Bayesian statistics, linking design and model-based approaches for survey inference, missing data analysis, confidentiality protection, and causal inference. So please join me in welcoming our speakers today. We're lucky to have them, and I hope you enjoy the workshop. Thank you.
All right, so thank you so much, Paul. So I'm Mike Elliott, as Paul introduced me. Also note that I think we're going to probably go to probably around 10:30 to 11 and take like a 15-minute break, so we don't just completely stay here for 4 hours. Of course, you should feel free, of course, those of you in the room, if you need to go out in between, that's fine. Okay, so I think that's the logistics. So we'll go ahead and kick things off here. So data integration, this is a big topic. We may do a whole course on this in the not distant future, and there are whole books in this. So we're definitely gonna just be screen disappeared. Okay, great. So, yes, so big topic. We're going to just be sort of hitting various highlights and various sort of tops of the mountains along the way here. So it's really more of an introduction, and hopefully if you find this interesting or useful, you can spend some more time digging down into the details. So, right, so why do we care about data integration? Okay. Um, so the issue is basically that single sources of data cannot often meet growing demands for high quality statistical products. So it's sort of both a supply and demand issue. We have access now to sort of massive amounts of data in various forms in ways that didn't exist 20 or 30 years, even 10 years ago. At the same time, there's interest in answering questions from this data that sort of methods that just require working with a single data source may not be sufficient. So basically, the idea here is how to make valid statistical inference from integrated data sources for a target population. So that's kind of the basic story. So some examples of this, multiple surveys. So we may have sort of web-based and face-to-face instruments, sort of main study refreshment samples, different modes, those kinds of issues. We may have surveys and administrative data. So often nowadays, some of the large surveys here at Michigan are combined with various data sources, such as Medicare data. So that's like 0.4, a special example too, I guess. The National Experimental Wellbeing Statistics, the Census Bureau is combining survey and tax record data and so forth. Commercial data, the more economics-focused studies now are using things like Zillow housing data to match up with the panel study of income dynamics sample. And then these surveys, of course, may be sort of traditional probability surveys, but they also may be non-probability surveys. So this issue of how to combine studies, and in particular how to use the strengths of the probability surveys to sort of fix up some of the weaknesses in the non-probability surveys, which may have their own strengths, like sources of data and particular data elements that don't exist in the probability surveys. So sort of combining the strengths and minimizing the weaknesses on both sides. And that's actually going to be probably the big focus, the thing we're going to go most into in this talk today. So again, sort of a generic overall slide here. We're not going to necessarily come back to this, although it undergirds a lot of what we're going to talk about today. The reason for integrating the data sets, the quality. So these can be whether the data is responsive to the user's analytic needs, right? Are they covering the information that we need? Are they covering the time period that we need? Sometimes they're we may want to have longitudinal measures. Are those available? Timeliness, how long the interval is between elements of the panel design, and how quickly they can be released for analysis or possible public use. And accessibility, right? Can users access this? Can they understand how they're supposed to do the analyses? Are we providing them sufficient documentation? And then coherence, whether the data are sort of consistent internally and externally with other relevant data. And then finally, to what extent they can provide sort of local or small area estimates within either using sort of traditional, if you will, small area techniques or just sort of more direct estimates in small areas. So again, just something to keep in mind as we go through the rest of the day's talk. So all right, so the specific things we're going to look at today are going to be looking at combining summary statistics through things like dual frame estimation. So this is typically the setting where we have two probability surveys and we're looking, or two or more probability surveys, and we're looking to combine them. And then microdata. This could be things like overlapping individuals as data sources, so record linkage. Talk a little bit about that. And then where it's unclear whether a given individual may overlap across data sources, but the data sources are in some sense targeting the same underlying population. And we'll talk a little bit about statistical matching and data fusion. And then we're going to go into a little more depth into the probability, non-probability sampling setting. So where we have a probability sample and a non-probability sample that we're trying to leverage the strengths of each. So, okay. And I should say also, Paul, please feel free to interrupt me. I kind of get going like a big, semi barreling down the highway here. So if
person reading the hunt.
someone has their hand up there.
Oh, is there?
Is there a question from
Jiaxu
Xiaoxun Zhao?
do you have a question?
No, let's just.
Okay.
If you've got a question, anybody out there, just go ahead and chat it into me.
Yeah.
We'll just kind of ignore raised hands for today.
Right. And yeah, so Paul, feel free to interrupt.
Absolutely, thank you.
Okay, so again, sort of just finishing up the sort of introductory piece here, I just sort of wanted to review what a probability survey is. And so this is going to be sort of critical to a lot of our underlying ideas about statistical inference and sort of connections that we're making with this integration issue. So probability survey sort of starts off to sort of define finite population. Could be very broad, like United States residents in 2020. Could be very narrow, third graders in the Ann Arbor School District, right? So there's some kind of defined population. The sampling frame that contains all elements of the probability of the population, and only those elements. So sometimes this is, approximate. So we might, if we're, let's say, looking at the U.S. population, we might sort of restrict ourselves to people who live in sort of standard dwelling units, so excluding group homes, homeless, and that kind of thing. And then, or possibly just households that have some kind of telephone connection and so forth. So, so the sampling frame gets, somewhat truncated relative to the true population, but it hopefully is pretty close. And then third point is that every element in the population has a non-zero probability of selection. Right? So there's some chance that everybody in the population and thus in the sampling frame, or so everybody in the sampling frame and thus hopefully approximation, at least approximately, has some chance of being sampled. Now those aren't necessarily equal, right? So folks don't have a lot of experience in the survey world setting. They may sort of think that when they say random sample, it's basically like drawing the sort of classic drawing balls out of an urn or rolling the dice or something. All the sides are equally likely to come up. We may purposely over or undersample some parts of the population, but as long as we know and have control over how likely we are to sample somebody, then we sell a probability sample. Of course, the reasons for doing that may relate to the fact that we want to get we have some minority elements in the population we want a larger sample of, so we can get more power to estimate differences between the minority and majority groups. It's there may be sort of other factors that are causing us to sample in that way. And I guess along the same lines, it's not technically part of the definition, but if you have a good estimate of if there's some sort of non-response or functionism that you don't have full control over, but you do have some idea of what's driving it and have to collect data on that, then you can same kind of approaches for dealing with the purposeful over sampling to deal with the stuff that's maybe somewhat outside your control. So, and I guess the fourth part is the random part, right? So that you can sort of define all the possible samples that can be obtained from the sampling procedure, and you select it via some randomized mechanism. Now, there are sometimes design features that go into this. So we sort of talked about the known probability of selection. So we can use things like weights as the inverse of that known probability, reciprocal of that known probability of selection to deal with the fact that we're over or undersampling people. So the weighted sample now is representative of what would happen if everybody had an equal chance of selection. Sometimes in practice, clusters are often done. So we may do a what's called a multi-stage design. So rather than sampling the individuals or whatever the ultimate sort of unit of analysis is going to be, we sample groups or clusters of those. So classic example would be if you're sampling students in schools, you might sample this rather than trying to literally get a list of all the students, say, that live in the state of Michigan and sample them directly. You might sample schools and then say classrooms within schools possibly. And so do that initial stage because it's It's both logistically easier. There's a list of all the schools in the state of Michigan, but there's no list of students, so it's fairly straightforward to sample schools, at least in principle. There also can be some cost efficiency. So in traditional area probability samples, where you're sending people out to knock on doors, it's far more efficient to sample, say 100 different counties in the U.S. and sample 10, 20, 30 households per county than it is to sample 3,000 households completely at random, maybe scattered across the United States in a less efficient fashion. And finally, there's this idea of stratification that's somewhat conceptually similar to the cluster thing, but where we actually have now sample some individuals from every single stratum in some sort of proportional fashion. So the traditional way, if we say it just worked on, we just had a sample of sampling a random sample of hospitals in Michigan, and we did some initial stratification based on sort of racial makeup of the mothers delivering at those hospitals. So we made sure that we had sort of a mix of not only stratified in race, and made sure that we had a fairly even distribution of at least of racial groups across our sample, but also implicitly in that would be things like urban and rural. So that kind of approaches. So okay, so again, many of you are familiar with this, I assume, but maybe not everybody. So we're trying to roll bases here. All right, so sort of get into our first example of data integration, dual frame estimation. So this is where we have several data sources to estimate a measure of interest. And I guess implicitly here, we're usually thinking about probability surveys. So they may be overlapping frames. So things like face-to-face and online panels, or cell phones and landline phones becoming less prominent as landline phones completely disappear. But until recently, it's a fairly common dual frame setting. We assume that basically the surveys are essentially identical, or at least the variables that we're concerned about are measured identically. So I'll do a little bit. We'll be doing sort of bits and pieces of math here along the way. So and probably a little more on the coding side when the Azure one gets up here. So, but we do have right. So our first math symbol today. So if we know how the population is distributed across the frames, so basically if we know that we have one frame, right, that has n sub A elements of the population, another frame has n sub B elements only, and then there's an overlapping piece of n sub AB. So could be that there's, if we sort of think about the cell phone landline example, we have a certain fraction of households in the nation that are only have landlines, a certain fraction only have cell phones, and some fraction of households have both. So that would be that would correspond to those A, B, and the A sample, the B sample, and the AB sample. So we get an estimate of our quantity of interest here for focusing on like population total. So we get the mean in the A group, say the landline only group, and then we get an estimate in the cell phone only group. And then for this piece here, kind of maximize statistical efficiency, we get a mean of the individuals that are so we go to the AB group and we look at the individuals that have I'm sorry. So this is a, yeah, okay. So basically here we look at the combined group. So we take all the people that are in the combined group and put them with A and get an estimate of that mean. And then for this group, we take all the people that are in the combined group and add on to it the people that are only in B and get an estimate of the mean. And then we put those together in an additive form, weighting them by this factor P, which basically sort of, if there are many more subjects that are sort of in the A group with the AB overlap, we weight those up, and if it's the other way around, we weight those down. If they're about evenly distributed, we essentially take the mean of 2. So, right, so that's basically the idea there. And often we don't know the size of those frames, so we have to estimate them. So we might know the overall things. We don't know in advance who has both. Now, in the cell phone example, you might have a chance using things like the NHIS actually does ask about that type of coverage. You could kind of at least get good estimates of who's split out, but often you may not know in advance who's overlapped. So you might have to find out during the study itself. So in this case, basically they give a sort of variance on the previous estimator. Now where you essentially subtract off the subjects that we think are going to be overlapped, and to get a pure sort of A only group, and then a pure B only group, and then an estimate of the true overlap size being there. So going in a little different direction, really trying now to segment out the population, or the pure A, pure B, and the overlap piece. And then to sort of minimize the variance, they use a little bit of a different weighting structure. That's basically sort of it's a quadratic. So this all just assumed essentially simple random samples within each of the population designs. There's been further work to extend this to more general sample designs, replacing the simple random sample estimators with design consistent estimators, and so forth. So that's just a little introduction to that literature there. Maybe I should just pause here. Are there any? Nobody's got questions coming through.
Nope, chat's clear right now.
Okay. All right. So, so we'll talk a little bit about record linkage. And this is a situation where we have 2 data sets where we think there are overlapping records. So it may be between sort of surveyed administrative records. So we know that, say, everybody in the population may be the administrative records, or a very large fraction of them. And then we have a survey of that population. So we think that we can find the individuals in the administrative records to link up data. So a classic example of this, as I mentioned earlier on, was looking at matching Medicare records to individuals, say, in the health retirement service study. The vast majority of Americans or residents have Medicare if they're over the age of 65. So we think that everybody over the age of 65 in HRS should be linked to those records. Now, it's kind of trivial. We have high quality unique identifiers, say Social Security or tax ID numbers, university IDs, and so forth. Right? We just sort of deterministically link those up. Where the statistics comes in is when we have common elements whose distribution is hopefully unique or close to unique. So things like names, address, birth dates, and so forth, for example. So we might not have, in the example I gave with HRS, you may have Social Security records, but only for the individuals in the survey who are willing to give their Social Security numbers. Not everybody's able to do that. So there may be a subset of individuals that we have to then try and link in different manners. We may have things like the birth date or where they live, and then we have that also in Medicare data, and so we can try to do linkage there. But there may be, on the next slide, there may be typographical errors or misspelling of text fields, right? And positions and days and months. So maybe somebody use the European style of month and day, of day and month, rather than the US style of month and day, or ambiguities due to nicknames or spellings. So, basically, each lengthening is assigned a probability of being correct, conditional on the observed data. So, if you fail to accurately link, you may get biased results. Subject to more errors and ambiguity may be sort of systematically different from other subjects. So it's a little akin to missingness, right? So certain types of subjects have more error in their attribute records, then they may be more difficult to link, and so you may miss linkages in some kind of systematic fashion. So that's kind of the issues around this. And so this is a little complicated. I'm not really going to get down to the details of this, sort of try to give a concept on this. But one approach to this is to use Bayesian methods, essentially sort of turn this as a big missing data problem and then pushing it into the missing data machinery, which has a sort of underlying Bayesian, typically has an underlying Bayesian approach to statistical inference. So, let's assume we have K files. We might just think K is 2 here, with P fields in common. So there's maybe say half a dozen measures like address, name, birth dates, and so forth. And they're all categorical. Maybe highly categorical names, for example, or maybe just things like month and year, birth date. But in any event, they're not continuous. We can categorize. And our only real observed data here is basically this X measure. So basically have so I would index whether they're in the data set they're in, so maybe just 1 or 2. And then J is sort of the element in that list, so the actual subject measure, and then L indexes which attribute you're trying to match up. So we're then going to think about there's sort of an underlying n number of true records here, and we can index each record, each data set, and each record then has this underlying true record number associated with it, right? So we're just going to sort of implicitly think we have 1,000 individuals on this record list. There's those 1,000 individuals on the first list, 1,000 individuals on the second list, maybe more than 1,000 individuals that are on those lists. But these are the ones that are going to be linkable, and sort of the underlying true population. And so we sort of use Y to be the true value of that individual, and Z to be an indicator as to whether or not the X is correct or not. So basically, incorrect or not. So basically, Z is going to be equal to Y, or correct. And otherwise, it just comes out of this sort of messy multinomial distribution, which is basically indexed by the category that they're in for that attribute. So, it's just some noise, whether it's not equal to what we're actually So we assume that this underlying Z has some it's a Bernoulli 0, 1, can differ by attribute, but importantly is the same across the two studies. The Y itself, right, has this multinomial distribution, right? Everything here is categorical. And then we put on some priors, because we want to be Bayesian here. So, sort of standard Dirichlet uniform priors. Probabilities for the multinomial distribution for the data, and for the actual probability of correct linkage by attribute. So all these quantities, including the n, are unobserved, except of course for x, I guess. But we can fit using Bayesian Markov chain Monte Carlo methods. And it sort of seems maybe a bit magical here, but there are a few assumptions that are required to make this model identifiable, right? So I kind of hinted at before that the error rate for a given variable has to be the same regardless of the observation list or the list, right? So there's sort of an underlying error rate that's assumed that really only depends on the particular attribute. And the distribution of the true values, again, doesn't matter which observation it is or the list. So that distribution of true values is the same across both lists. So, and that all the linkage structures indexed by this lambda are equal. So under that, we can identify this, run the model, and then basically look at the proportion of the MCMC draws where the lambdas are the same, right? So there's some underlying, this underlying indexing thing is going to be the same. And so then we just tie those together. And so basically for each observation in if we think of I as 1 and M as 2 here, basically sort of take an observation from the first data set, the jth observation, and then we can then look across all of the observations in the second data set and assign them some probability of linking. So hopefully there'll be a few observations with a very high probability, and most of the rest will have very low probabilities. But that's the whole point of the linkage, right? So there could be some variables that it's very unclear which one they should be matched with, and others it'll be very high probability. So that's basically the underlying idea. Again, I'm sure we could probably spend a couple days or more, a couple weeks going over this literature, 15 minutes. But again, at least an introduction if you haven't seen it before. Okay, so a little bit more in this area, I guess. If the number of records is large, maybe more than several thousand, this can be kind of impractical because it's basically the sort of computation is sort of quadratic in n, right? Each observation has to be, each subject in a given data set has to sort of be compared with all the other subjects. So if you have a million records, that may be impractical. So so this idea of using blocking, sort of maybe doing it, it's sort of a straightforward approach to sort of pre-match based on one or more observed attribution of blocks. So you're sort of saying, I'm just going to forget about the probabilistic part, at least on a few records, a few attributes, and I'm just going to treat them as deterministic. So you have to have the same birthday, for example, same last name, before I start looking to match on other things. So of course it then creates this risk of false negatives. You're back to this issue that you know, because you're not allowing some chance of subjects to be matched based on error. Then if they're across blocks, then essentially you sort of have sort of this of so-called false negatives. You know, some subjects that aren't matched when they could be. One way to kind of get around this a little bit is this idea of multiple blocking. You kind of create sets of overlapping blocks that increases the computational time, but it does reduce your risk of false negatives. So, 0 because there's always some. That's a better piece in terms of the practice of actually doing record linkage. So the next piece we're going to talk about here is statistical matching or data fusion. So I'm not sure why it got this name, statistical matching, because then it doesn't involve the matching or linking of records, right? We just talked about record linking. You might think statistical matching, that's got to be pretty similar. Sounds like probabilistic matching, but it's not. So this is where we basically are in settings where we don't think there is actually much overlap. There are few or no records that are believed to occur in both data sets. So we may have, again, 2 independent sample surveys, small sampling fractions. But we're in the situation we do have some overlapping covariates and then some that don't. Right? So basically, a little picture here. And so just sort of a little toy example here. We might have a couple of surveys, one of which has a lot of information about heart disease, the other one of which has a lot of information about nutritional intake. And we'd be sort of interested in trying to see, is there some way to kind of link this information about nutritional intake to heart disease? Well, if there's no overlapping covariates, the answer is no, right? If that this middle box, this middle column here are empty, we can kind of do. But if you do have some overlapping covariates, so typically surveys pick up some demographic measures, I assume would be common to both and maybe other things as well. Then you have some hope to undertake this matching or fusion approach. So typically some kind of independent sampling between the two samples. And we can kind of think of survey B here as a so-called donor data set. It doesn't really, you kind of switch it around either way, but for purposes of explaining what I'm doing, we're going to think about this as the donor and this is the recipient data set. And our goal is to kind of get this joint distribution of X, Y, and Z. For inference, and in particular, we probably really want to start making inference about X and Y together. We have Z in there to make this work. So again, a very large literature in this area. I will, I'll just sort of hit the high points here. The high point two. Okay, well, I guess this actually is where the matching idea does come in. It's not because you're actually directly matching an individual, but you're trying to create a sort of statistical match, a sort of equivalent observation in one survey to the other. So you want to find observations in survey B and in survey A, where the underlying Z's ideally would be identical, right? And then to essentially donate or impute the X value up to survey A to kind of get a joint, get this joint XY and Z then survey A. So now you may have some situation where you have multiple observations where there are many possible donors. We might have to switch here. Perhaps it should be multiple B's for A. But in which case you can choose one at random. A more common situation, far more common situation, is that you have no observations. Right? Z is pretty rich here. You like Z to be as rich as possible. It's unlikely that you're going to end up with two individuals that have identical Z's, or at least it's not going to be common. So you're going to have many situations, not all situations, where you're not going to find an individual that has this exact image. So you construct a distance measure and choose the ith observation that minimizes that distance measure. So that distance measure could be, again, I guess we didn't engineer it, could be Alnova's distance, sort of trying to look at some kind of variance adjusted, sort of trying to normalize these variables to be of similar mean and variance, and then look at the differences between the different Z values and finding those that whose normalized differences are as small as possible. So doesn't have to be normally distributed. Categorical variables work fine for this, particularly with large categories. There are a variety of distance measures. I'm not going to spend a couple of days on this, but that's conceptually the idea. So now, why does this work? Well, if we have same design and then the resulting joint underlying distribution here, the X, Y, and Z, we can write this out as joint distribution of X and Z times the conditional distribution of Y given Z. So if we have this conditional independence between X and Y given Z, right, this underlying idea that we have these independent samples, everything's working the same in both samples. So once we condition on Z, we should be able to sort of break this relationship between X and Y. And we have sufficient information in Z to do this. And so if you get this situation in place, then you can kind of rewrite this as looking at the joint distribution of Y and Z given the conditional distribution of X given Z. So if we condition both sides on Z, then we can take this last part here. Sorry. Condition that out and get this distribution here. So essentially, the marginal distributions will remain the same after matching. Okay, so distribution of X given Z and the distribution of Y given Z are in. So the joint distribution depends on how reasonable this assumption of conditional dependencies. Right? So this all boils back to the idea that we have a similar design, and so this resulting distribution. Okay. So, how are we doing? Any questions?
Nothing so far.
All right, so now we're going to kind of get into the last part here, which is where we're going to spend the bulk of the rest of, pretty much all of the rest of our time today, particularly because that's where Yajwan's going to be going over the examples, which is it's just integrating probability and non-probability sampling. So I guess it kind of firstly, this kind of relates a little bit to the idea of statistical matching, but suppose the quality of the surveys A and B are different. So go back to this. We sort of assume that the sort of underlying associations here are the same. And we have two probability samples that are reasonably high quality or similar quality. We would expect that to be the whole. But often that may be not the case. In particular, let's suppose we have a survey A, which is an outcome of interest, is a non-probability survey. And then survey B is our probability survey. So, of course, we extend this to settings where the missing Y or the missing X are observed. Right, so we have a little picture here. Right, we could think about one of these being probability, one of these being non-probability. But it could be a situation where all the X's and Z's are observed in both surveys, or even where everything's observed. But one of them is a probability survey, presumably of high quality, and the other one is a non-probability survey, or probability survey of lower quality. So, so the really concerns are about selection bias. So the availability of data from a probability survey that allows the possibility of using information from that sample to adjust for the selection bias in a non-probability survey. So this is basically the idea that we're trying to take the information from the probability sample to adjust the non-probability sample to improve its quality, improve its informational properties. So may not make it perfect, right? We're not, often in real world situations, we can't fix all of the issue. Hopefully we at least fix some of it. We've worked in missing data before. All this is going to be very overlapping in terms of somewhat similar ideas to missing at random, missing completely at random, missing not at random. And so you might say a situation where you have sort of missing partially at random. So there may be some components when you condition on the available covariates to adjust for the missingness, the fully observed covariates to adjust for missingness. You may reduce part of the bias. There may be a component that remains, but getting a partial fix is better than so. So that's basically the sort of underlying idea we're going to tackle here in various ways. And in particular, we're going to talk about two approaches for this. This idea of quasi-randomization or pseudo weights. sort of the non-probability survey, we're going to assume maybe has some underlying probability mechanism or something that could be viewed like that. So we're going to try to sort of recreate or estimate that underlying selection mechanism and then treat it as an actual selection mechanism. And then the superpopulation model. So this is more of a prediction method. So trying to use the available covariates to predict outcomes, and then use some prediction method for this. Nowadays, I think we tend to rely on things that are pretty robust. So things like BART or Mr. P. Sort of Bayesian multi-level version of post verification that's measurable. So yeah, so I think those are the main approaches. So there's a third approach, potentially things like matching that hasn't been used quite as heavily in this area, but we're also talking about that. Okay, so all right, so basically in quasi-randomization, I kind of mentioned this before. The basic idea is we're going to combine probability sample, non-probability sample, to estimate the probability that the non-probability sample data would have been selected. There are several of those probabilities that just be used as a regular sample weight. So one thing, I guess, just to go back slightly, I mentioned there is these two approaches. I think do have they're somewhat tied to the particular problem at hand. So quasi-randomization is a good way to try to create weights that are not particularly tailored to any one particular analysis. So if you're sort of trying to create some sort of public use data set where you sort of try to fix up a little bit maybe some of the issues in the sample, this is one approach I think that's pretty commonly used. If you have a more targeted analysis, so in particular, we're going to things like if we have a randomized trial, we're really focused on a particular effect of a particular treatment, then more the modeling approach has some potential gains in efficiency over the pseudo-weighting approach that's may make it more appropriate there. Okay. Right. So that. All right. So we have a couple of scenarios we'll look at. One is where the outcome is only available in the non-probability survey. Right. So we have some we have some outcome Y. So black means basically it's observed, right? So we have some outcome Y. It's only in the non-probability survey, not in the probability survey. We have a bunch of covariates X. We observe in both surveys. But in the actual sampling probabilities, we only know for the probability survey, right? So we don't know these weights in the non-probability survey. So, right, so there's some references here that have reviewed sort of existing approaches for non-probability surveys. So let's suppose our target population, sample size capital N, we have the study variable of interest Y, and our auxiliary variables X. Right, so in the non-probability survey, we have both Y and X observed. I'm using this NP as a note. SNP means it's the set of individuals that are in the non-probability survey. And then we have a binary inclusion indicator. We included the non-probability sample, and it's kind of defined for all units, right? So there are some assumptions here that are pretty critical. You see there's a lot of, if you do anything in causal inference also, you'll see there's some overlap with that work as well. So there's basically some key things that we need to make inference with these non-probability sample units. One is positivity. One is that basically all population units have to have a non-probability, non-zero probability included in the non-probability sample. So almost by definition, that fails. Not always, but there may be some components of the population that are excluded. So we'll have to hope that, essentially with respect to the covariates that we do have, the data we do have, that there's no discrepancy, that the distributions are the same as sort of the elements that sample was 0. But for the math to work, then I'm going to have to make this. Independence. So the inclusion indicators are mutually independent of each other, given auxiliary and survey variables. That I think are reasonable. The indicator and study variables are independent for a given set of covariates, right? So that basically means that we're again conditional on X, and we sort of are able to start treating these things like a probability sample, or the distribution within and straight of X of the Y are going to be the same in both the probability and non-probability sample. That X could be very high dimension, so the use of prediction of weights and so forth is critical here. So the higher dimension of X, the better we are, the more likely we're able to make these more abilities. And finally, we have this, that we do indeed have a probability sample with information on X, but not on Y, that has sort of this overlapping set of covariates and sampling weights that are associated. So again, to kind of bring back the picture here and add in the non-sampled pieces, right? So we basically have a probability sample, more or less overlapping non-probability sample, and we're basically sort of trying to use this piece here, sort of get an idea of what the non-sampled units are here, and to essentially fill in Y's across. So there's a couple of approaches for this. Basically, we want to use this reference probability survey to get the distribution of the auxiliary variables. Either estimate the model for propensity score, basically get an idea of the non-probability probability of this individual having made it into this empty sample. Or we can do a prediction. Predict the outcome of the population units and so using some sort of outcome model for Y given X. And then finally, we can put the two together using so-called doubly robust estimators. So the inverse propensity weighting approach, pretty straightforward. And conceptually, basically requires that we estimate this inclusion of probability for the non-probability sampling elements. And once we have that, then we just take the reciprocal, that becomes weight. So, sorry, a little typo here. I think there should be an I. I've seen the pies. Right, so each individual, right, reciprocal multiplied by Y, divide that by the sum of the weights. So this so-called Hayek estimator. Again, just what you would do with the probability sample piece, but now you're using this estimated pi. So that's all well and good. How do we get that pi? So there's a couple approaches. Work that I did a while back basically sort of showed that you could create pseudo weights by looking at the odds of being in the probability sample relative to the non-probability sample for all the elements in the non-probability sample. So basically combine the probability and non-probability samples and run a logistic regression using the indicator of whether or not you're in the probability sample as the outcome, and then using the X, common X's in the regression model. So from that you can get that probability, from that you can get the odds, and then you have to multiply it by this piece over here, which may or may not be available to you. If you know the design of the probability sample, and if we have enough information in the probability sample directly compute the probability that that individual would have been sampled in the probability sample, then you take that weight and multiply that by the odds. you don't have that information directly, you'll have to try and estimate it using the available covariates. So basically do some kind of regression of the weights in the probability sample on the X, available covariates, and then use those predicted probabilities in place of the true ones here. So a couple things here, I guess, to note. One is if the probability sample itself is basically a simple random sample, these are constants. So basically the whole thing evolves down to weighting essentially by proportion to the odds of being in the probability sample. And conversely, if the X's are basically saying that the non-probability sample looks like the probability sample, right? So this ratio here is about 1, then you can just basically use whatever the equivalent weighted value would be for the given covariates for being in the probability sample, then sort of put that back into the weight. So there's sort of logic to this, and so gets you reeling yourself back to ideally, if you have all the available X's, you got the model right, back to the true probability of this true INP. So, so we kind of use logistic regression, some earlier things. I had some later papers with a student a couple years back. Used Bayesian average regression trees to estimate these pseudo weights, and really did pretty well. Again, you need the X's to make this work. So an alternative approach, a little more non-parametric, estimates a maximum likelihood function. Basically treats these pi i's as unknown and combines the data from the probability and non-probability sample using this likelihood function. So a pseudo likelihood function. And then estimates the pi heights that way. So okay, so that's basically a couple different approaches that we can look at. So related idea is calibration. So rather than if you have, particularly if you have outside information above and beyond the probability samples, so you have census data or things like that, then you can balance sample sizes within the population sizes, join contingent samples to adjust to the full process population. So it turns out that it's often unfeasible due to smaller empty cell sizes or some unknown joint population distribution, in which case calibration is a generalization of post-stratification that minimizes the difference between the sample and the population. Ranking is probably the most common calibration method, which generates weights for each case to match the population margins. So, so that's there are some sort of more generalized forms. The developments Arndell paper has great sort of introduces this idea in a very broad and general fashion. So, so that's an alternative way to try and do adjustment for your sample. Okay. So to generate weights, generate weights to adjust the non-probability sample. Okay. Again, follow along. Questions?
That's good.
Okay. So the last piece we're going to talk about here, before I hand it over to Yashwan and we'll take a break, is the model-based predictions. So this idea basically is to use parameters based on the non-probability survey and auxiliary information about the population to predict the population outcome values. Right. So So we have some model for y, we have an x. And the idea being now that because we know the probability survey, we know what the distribution of x should look like in the population. And we can use that essentially to do prediction across the population, right? And thus make inference. So that's conceptually the idea, again, pretty simple. Flexible models, machine learning algorithms can be used as a computation engine. So there's sort of traditional multiple imputation ideas here, or use these sort of mass imputation ideas that come out of so some examples. So integrating the Pew Research's political survey, which is a non-probability survey, the current population survey, high quality federal government survey. So again, they have some information about political attitudes and so forth of the government. So an obvious reason so to collect. So they can do it as a private form, and they do it more cheaply using non-probability convenience type sample. Got our overlapping covariates, fairly rich set of overlapping covariates, and so we can sort of apply these methods there. Okay, so to sort of continue down the sort of prediction approach, this multi-level regression and post-stratification idea, Gilman and Little sort of produced this back in the late 90s, and then followed up on particularly with Yashwan's work here in the century. So some of the very famous example used state-level public opinions from social demographic groups using sample surveys. So they sort of had two key components. One is they use a multi-level regression for small area estimation to get a prediction model with a large number of covariates using sort of regularized Bayesian prior stratifications to kind of stabilize estimates. So the idea here, they're sort of borrowing, I mean, we talk about small area estimation, and we always think about it as being geographic, but it can be used in other settings as well. So you may have, take the demographics, for example, you could imagine putting these over brought to the tables. So if you have sort of age, gender, education, you might end up with, you have, say, 5 or 6 age categories, 2 or 3 gender categories, 5 or 6 education categories. You know, you're sort of looking at 100 or more different cells. And so you can use these sort of smoothing and small area estimation techniques for estimation in those cells. You don't just have to rely on correct estimates. And so that's sort of the first piece of this. And the second piece of it is we've got some post-stratification. We have some way of adjusting. So now we think are sort of pretty good estimates within the cells, but now we need to make sure those cells match the population. So we can essentially also line this. The non-probability survey is sort of where, and one you can correct me, but I think that's where most of this works, and most of the information from this is going to happen, right? We're sort of taking this, we have very granular, deep information here about this relationship between y and x, and we assume that holds no matter whether we're getting these people from Xbox users or from the general population. So we're able to kind of get that piece there. But now the actual distribution of X is being very weird in a non-probability sample. Xbox users, because this was actually one of the first really cool applications of this. So it might be that, you know, they have 8 times as many young men as the general population, 1/20 as many older women. But there are few older women in there using Xboxes. And so we're able to kind of reweight then, or readjust based on this post-stratification to correct for the imbalances. So really nice example of how you're leveraging the two sources. So the first, the big strength on the non-probability piece is doing this. The big strength on the probability piece is doing this. So you're able to take the two strengths and throw away the two weaknesses. So,
I have a,
Yeah,
excuse me,
sure.
I do have a question there. Should we be thinking of the non-probability sample, or really either sample, as should we be thinking about these as kind of two complementary pieces, like to the extent we've got control over the non-probability side?
yes. Yeah.
That is the key, that's the key. We're not trying to build two representative samples, right?
No.
We're trying to kind of build two opposite samples.
Right,
that
we're trying to take the strengths of
Okay.
each. Now, very often, I mean, to some extent, the non-probability sample would be sort of like found data, right?
Sure, exactly. Yeah.
So it's, you don't have much control over that, except perhaps what you choose.
Right.
But yeah.
Yeah, cases where we've got some sort of control, either like we can choose from a list or whatever.
Right.
Okay.
So typically, when you're in a situation where you have some data, so I mean, again, slide. You have some whys here in this Pew study, right? So they asked a whole bunch of questions like, what's your religious background? You know, how many religion may influence your political voting? Right? CPS tried to ask those questions. You can imagine how that would go over. The government's trying to find out about your religious behavior,
Right.
and how you vote. So can't do that. But they also ask a whole ton of questions that are highly related to why that government can ask about risk questions. So we know the distribution of X from the CPS. We know the relationship between X and Y from Pew, and so we can use the former to adjust the latter to get marginal distributions of Y, or perhaps even conditional distributions of Y given X that may be less refined than the ones we're using to actually do the modeling. So again, the missing data analogy. If your underlying sort of deepest level relationship between X and Y is what you're interested in, you're not going to get any help from this because all that information is encoded up here in Pew. CPS isn't going to help you. To the extent you start trying to marginalize this, right? So now you want to just look at like either more broad associations between, say, political beliefs and education, sliced into 100 different categories, then or just overall political beliefs or overall religious measures, then this approach, right, fixing the Y's, the distribution of X to well. So, and regardless of whether we're using Mr. P or whether we're using weighting, conceptually it's the same idea. Great. So, right. Okay, so I guess we just remove that.
Another question here.
Yeah, sure.
Are there situations where you would reverse the order in which you perform the steps within Mr. P? So for example, are there methodological advances to performing step 2 prior to step 1, and what might those situations be?
Would you mind repeating that? I'm sorry. I'm not sure. I'm sorry, Mike, if you just make sure to get
Okay,
that.
so if I can, so you're asking basically, we put this out in kind of an iterative fashion, right? We said there's step 1 and step 2. And you're asking, is there some advantage to doing step 2 and then step 1? Well, even though we kind of, I mean, there is kind of, I know I do think the order here matters in the sense that the information about 2 is really just coming from the population, from the probability sample, from the population data. So, so you really have to have 1 done first before you can apply 2, I think. Anybody else? Okay, so, all right, so I think when Yajwan gets into her example, she'll probably get this in a little more detail, but basically the idea here is you may have, we talked about this post-stratification, and implicit behind this is you've got all the sort of interactions in place, right? You're sort of looking at all the, if I mentioned the age, gender, education things, you're sort of looking at the full, 6 by 2 by 6 table or something, right? So, what the Mr. part of Mr. P involves is this multi-level regression, which is essentially using a shrinkage approaches. So you put the interactions in there, but if the data don't suggest that they're important, you sort of shrink down their value, right? So you start to sort of smooth or collapse these greater to some degree. So there are sort of different ways to do this. There's Gaussian process regression models, machine learning algorithms, and so forth. But that's sort of the basic idea there. And the key to success is the existence of highly predictive auxiliary variables. So in the example that I was sort of alluding to earlier, they were looking to adjust Xbox users' predictions of voting. I think this was like in the 2012 election, to try and estimate the voting behavior marginally in the whole U.S. population. And so basically they had a whole bunch of things, including people's attitudes, sort of whether they identified as Democrat or Republican or independent, religious measures and so forth that went into the Xbox data. And they had equivalent data from a previous election looking at the distribution of those kinds of measures amongst voters in 2008. So they basically sort of try to match the 2008 data to the 2012 Xbox data. So we kind of readjust these highly, it's very dense, highly refined set of highly predictive, importantly, auxiliary variables to match the sort of population distribution. And then from that, use that to predict the ultimate outcome of interest, which is who you're voting for. So, so they were able to, and again, it's highly predictive because once you get into things like party identification, that's very important. Not perfect because there are Democrats that go for the Republican candidate and vice versa, but those kinds of things become highly predictive. So you can fix big problems. This example, marginally, Romney would have probably won quite substantially. It was a heavily male sample of Xbox users. Did not. And predicted values matched very closely to the percentage of votes that Obama actually got. So, so I guess the last point here, this auxiliary information may be only partially collected and require modeling to get the synthetic population distribution. So that was not the case in the example that I talked about, but it might be in other settings. So, all right. So the last thing we said we were going to mention is this idea of doubly robust inference. And it basically tries to use combinations of the prediction method along with the inverse probability weights for the survey outcome and provide protection against either model misspecification. So, right, so behind all this, we've sort of written down models, some sort of somewhat generic fashion, right? So we had models here. Have a model here. Right? They can all be misspecified. So sort of modern machine learning regression techniques and so forth. That's critical, but can still happen. And so the hope would be that if one's correctly specified, or at least quite close, and the other one may be far off, that you can kind of fix one with the other. And that's basically the idea. In the Chen approach, they combine their probability, non-probability surveys, basically looking at, right, so you have this, again, Y is not in the probability survey, so they're predicting it, right? So they get some predicted estimate of Y just using the probability survey. And then they adjust that by looking at essentially weighted residuals from that prediction. So, so essentially, what's going on here is if this model is correct, if mu hat's correct, right, then this will be an unbiased estimator, and this difference here will be 0, and so this sort of correction piece will go away. Conversely, if mu hat is biased, there's some sort of bias piece in here. This estimates that bias opposite direction, and adding them together will give you an unbiased estimate. So that's sort of conceptually how the bias estimation works. Okay, so just to kind of revisit these assumptions, right? We do need to make fairly strong assumptions to make inference with this non-probability survey. Essentially, the sample units are exchangeable. The non-sample units, the same share the same measured characteristics. Right? Then, in some sense, the non-probability survey becomes probability survey when you slice nets anything up. No parts of the population are systematically excluded entirely from the sample, or if they are, they're essentially exchangeable with the ones that are. And some examples that I worked in, this last one was quite problematic because they were looking at driving behavior, and they were only looking at automobiles in a few states. So you essentially had to make an assumption that whatever kind of driving behavior you were looking at, Tennessee and Alabama, if you wanted to make a reference to the whole U.S., that behavior was basically once corrected to look like Alabama, and Tennessee would look like the U.S. as a whole. Again, within variance. So there may be more rural drivers in those states, but you know, adjusting for that, the young male, high school educated rural driver in Alabama was essentially exchangeable with somebody like that from North Dakota or California. And finally, the composition of the sample units with respect to observed characteristics either matches or can be adjusted to match the composition of the population. Basically saying that you have the axis available. So another scenario is where the outcomes available in both surveys, right? So we may have essentially everything picked up here, but we might want to integrate this information from the non-probability survey in a way to add more power, more statistical efficiency. So there are a couple of approaches for dealing with this. I'll just touch on them. One is that we can kind of, right, the only missing part here now is the weight. Right? There's nothing that really penalizes from using y in this prediction of the weight, right? So essentially for that probability of mean and the probability sample, when we combine the two samples, just add y into that prediction. Just weight is the weight. It's nothing magical about it. An alternative approach is to use the non-probability sample to construct a prior for the probability sample when estimating regression coefficients. So again, if the sort of regression coefficients are the same here, right, then basically we can just sort of combine the data and call it a day. So the idea of this approach is that you allow for less than full combination, right? You sort of treat the non-probability survey as lower quality, and so you sort of it sort of contributes less information to that estimation procedure, but still some. So right. So now I'm just going to sort of finish up with a sort of a general discussion, and then we're going to move on, take a break, and then move into sort of the indicators of actually making this stuff work. So I think so the headline here is the choice of the statistical methods is secondary to the choice of auxiliary variables. So really emphasizing the idea that the whole story here really to some extent is based on X, right? We keep talking about X is sort of a default for our overlapping covariance, right? So basically we've got to have adjustment approaches that include all the predictive auxiliary variables to get valid information. And so, in terms of variance estimation, I guess we haven't talked too much about that. Again, you guys want to basically there are sort of the usual things that we see in the survey world, linearization approximations, right? So using kind of generalized estimates to deal with the survey weights, sampling if it's available in relevant survey, replication methods, jackknife, bootstrap, and Bayesian posterior inference, which if we're using things like BART for prediction or for Mr. P, they both have underlying Bayesian approaches that sort of make it easy to build. And so, I guess as a last little example, this is sort of one thing I've worked on recently. It's sort of viewed as a special case of the probability non-probability survey setting is this transportability of randomized trials, the quasi-randomization and prediction approach. So it's a sort of a special case where our non-probability sample now are these randomized controlled trials, RCTs. So they have a great deal of use in the medical world and to some extent in the social science world as well, because they have a gold standard, including survey methodology. So they're kind of a gold standard for assessing causal effects because they can eliminate both observed and unobserved confounding, right? So essentially, the critical thing in causal inference is how your treatment or exposure is assigned. And if it's assigned totally at random, nothing can confound it, right? Because it, by definition, can't be associated with any confounders. So that's cool. And that's kind of the end of the story. But only to the extent that your sample is representative of some relevant population, right? So if there's the other issue is it's also fine if there's no effect modification, right? So if essentially the exposure works the same in all individuals, either systematically or with only random error, then you're also good. It doesn't really matter what your sample is. When I first got involved in STISH for a long time, I was always wondered why do people who are doing randomized trials not worry about, saying like in the survey world, why do they not worry about the population? Well, it must be because, and I don't think I would have expressed it this way initially, but essentially they sort of assume effect modification away, right? Assume we got some biological mechanisms working the same in everybody, at least not systematically different. And that may be the case for some things, but often not, particularly in the social science world, but even in the medical world. There's a lot of differences in how different treatments may affect individuals. And they may differ systematically, right? Certain types of individuals may have different effects than others. And so this idea of effect modification play an important role if there are systematic differences between the trial sample and the population of interest with respect to these modifiers. So even though you have the power of RCT, you can still end up with causal effects that are biased if you have effect modification and systematic differences between the trial sample and population. So transporting these causal effect estimates from trials to populations requires we have some sort of population representative sample. So again, integrating this non-probability sample with probability reference sample, it's just the non-probability sample is a randomized controlled trial where our real focus is this causal effect. So, okay, so kind of drawing the picture out here. So it's pretty much identical to what it's similar to what we had before, a little different because we're sort of now got a little more structure in terms of what we're thinking about the data. We still have this idea of these common set of covariates here between the probability and non-probability sample. Probability sample still has the weights. Now, our outcome of interest is in the non-probability sample, and we're sort of dividing this up in this causal inference world. So I guess just a very brief background on this. So the idea to make causal inference is sort of defined this idea of potential outcomes. So basically, you have some sort of this A here gives the treatment assignment. So the first half of my sample here, all the subjects were assigned to a treated arm. In the second half, they were assigned at random control arm, right? So we sort of random assignment here, just sort of things, sort of for the first half or the treated in the second half. Of course, they don't have to be half and half, although for maximum power, they typically are. So that's our non-probability sample. The probability sample, right? We have the X's, how to weight them. We don't know anything about the outcome, potential outcomes here, right? And so the treatments are kind of so you could have situations where you may have everybody in treatment. So maybe you have your sample, in some sense the control is sort of withholding something that's out in the population. More commonly, you might have the outcome observed for the control group, right? And only the people in treatment, so only the people in the randomized trial have access to the treatment. So there's a few methods for this. One starts with this idea of inverse probability weighting. So basically, very much similar to what we just talked about in the more general setting, basically trying to reweight the randomized control trial on covariates so the weighted distribution of the covariates matches that of the population. This idea of matching maybe plays a bigger role here because we sort of have this very sort of targeted inferential, very targeted inference that we're interested in. And so sort of trying to just picture here, you might try to pick off cases in the here. Pick off X's here, right? Kind of fill in their treatment or control from X. Probability sample piece. Outcome regression, right? So again, this idea is sort of now we're trying to sort of model the outcomes here based on X, and then predict down into the probability sample piece and thus into the population. And then doubly robust estimation, right? Sort of combining these weighting and prediction approaches. And so we reference some of the various approaches that are considered in the literature. So some of the key assumptions here. So randomization, right? Sort of meant by that it's not really an assumption, because it's meant by design. This idea of stable unit treatment value assignment, and the basically dependence of. So this is sort of getting a little bit into the causal inference world, but basically it means that whatever treatment gets assigned to person A will have no impact on the potential outcome for person B. So in many cases that's true. I mean, some examples where it might fail would be things like vaccine trials, right? If you're an unvaccinated person in a room full of vaccinated people, that might affect your risk differently than if you're also in a room of unvaccinated people. So that kind of in many settings that's reasonable. This idea of positivity. So here positivity means essentially sort of two forms of this. That both that everybody has some chance of getting the treatment or control, both in the randomized control trial by definition, but also if they were then moved to the general population. And also that, again, everybody in the randomized control trial, there's some chance that somebody in the individual population could have been selected for the trial sample. And common support, essentially that we have the X's that are available to ensure that. And finally, more ability, right? That this is probably the one that's unique to this problem of combined RCTs, that basically potential outcomes have the same distribution or global data sources conditional on covariates. Kind of related to what we just talked about in Mr. P, right? That you sort of have this, once you get a rich enough set of X's, then essentially the way the treatment will work will be independent of whether they were picked up in the randomized trial, whether they. So I just finish up. One of the examples that I worked on, I actually have a paper on this, and I think you guys want maybe some stuff in this examples. There's this issue that sometimes population average treatment effect of the treated is of interest. So now you're really focusing on individuals that get a treatment. So basically, if you sort of think there's some right, so in some sense, sort of trying to make inference. It's just the individuals in this piece here. Or the mid, like, or what would happen for individuals just in the treating. So again, causal inference background, but this is sort of the individual level causal effect, difference in these potential outcomes within an individual. And then we're going to start to average that across all the individuals that get treated. So that's the target. How do we estimate that? A couple different approaches. Inverse probability weighting. Again, using this concatenation, and I guess the extra piece here is that we might have population level data for the axis. So we could sort of put that all together and get this inverse probability of selection. So I think some of the examples use this. The paper that I worked on sort of extended this idea. Just the same example of the standard non-probability sample, sort of combining the RCT and the probability sample and getting the odds of being in the probability sample and then multiplying that by the predicted probability of being or known or predicted probability sample for the RCT units. And then for prediction, basically under randomization, we can basically, and ignorability here, we can assume that we are able to predict out. Well, under randomization, we can certainly predict y given x for potential outcomes. And then under ignorability, we kind of replace the need for the treated subjects or for the subjects assigned to the control group in the probability sample. And we can use things like Bayesian average version trees to get robust predictions. Or predictions of them. Okay, so, right, so then to actually get this estimate of the PAT, probably we should have a little hat here. So we can combine or thread. We can combine the non-probability weights in the RCT. So basically, try to weight the RCT to look like the probability sample, and then compute the difference between the observed treated outcome and the predicted control outcome. And then if we could, because we have information on outcomes in the probability sample piece, we can add those in. The example we actually looked at, we actually had essentially the outcome for the treated and the probability piece as well, so we can predict that. And this can add on the RCT, which may or may not be a non-trivial part of the population of interest. And then use, if we're using BART, we can use sort of Bayesian posterior samples or multiplication, so a combination thereof to get variances. Okay, I think we're at a point where you can take a 15-minute break and things over to Joshua. As I said, I don't think you always say we're not going to go to one, but I don't know. Maybe we will.
You mean at this time?
Sort of on the low end or the shorter end.
That's fine, yeah.
So we're more or less on schedule.
So what time?
I guess before, any questions? Yes.
Like in your last slide, how would you do some kind of sanity check that the model that you use to generate the predictions of your counterfactuals is, correct? Would you try to,
So,
maybe, I don't know,
Yeah.
a bit open.
no, you're absolutely right. And actually, in the paper we worked on, we were able to do that because we actually do have this information on the non-probability samples, on the probability sample side. So we did some posterior predictive checks. So you can't totally nail it down because you only get one side of it. But it gives some evidence that we actually did have some bias. We actually sort of had a little bias correction piece. Otherwise, I think you're a little bit, because if you're in the you're in that situation, I think it's a little trickier because you essentially have, all the information about X and Y is going to be here in the RCT. So that's why using the sort of most robust prediction method. However, no prediction method can fix missing X's. So. Any questions?
From the chat.
So, yeah. All right, so 15 minutes, we like around 10 to 11 or so?
Sure.
5 to 11. Okay.